Okay, so to kick off the second half of our session here, we're going to have Robert Zubrin. He is the president of Pioneer Astronautics, an aerospace R&D company, and formerly at Lockheed Martin, where he was responsible for developing the Mars Direct concept, which is a really exciting, low-cost Mars mission concept. He's also done a number of other really cool things, and we're really happy to have him, so welcome.
Thank you. Okay. So I'd like to thank the Breakthrough Institute for inviting me to come and present here. I'm going to talk about a new concept for space propulsion and for propellantless space propulsion. Okay, and it's called the Dipole Drive. Okay. Now there are a number of concepts out there for propellantless propulsion. Solar sail, we've heard about it. It's the most established. It goes back to Tsiolkovsky. And we'll hear more about that. Electrodynamic tether, which I won't discuss. The Bussard ramjet, 1960. Robert Bussard proposed a method of interstellar propulsion, which was very exciting. He would use a magnetic field as a kind of scoop that, as the ship went along, it would scoop in interstellar media into a fusion reactor, produce thrust, and it wouldn't need any propellant. And it had two problems. One was it needed its giant scoop, which was thought to be a magnetic field, and the other was how to do proton-proton fusion in a starship. But in principle, there it was. Now, and as Bussard commented in the close of that famous paper, nothing worthwhile is ever easy. Well, there it sat until 1987, when Chu developed high-temperature superconducting wire. And that inspired Dana Andrews to look at making a magnetic scoop. And he didn't want to have to address the question of proton-proton fusion, but he started to make a giant magnetic scoop to bring in the ions and then use them in a conventional ion drive. And so while it wouldn't be generating its own power, it still wouldn't need any propellant. But what he was getting was that the scoop was generating more drag than thrust, than the system was generating thrust. And so he called me in, and I was at the University of Washington at that time. So all the developments in magnetic sails were done by people at the University of Washington. Myself in the late 80s, Wingley in the late 90s, Slough in the next decade, and we're due for one right about now. Okay, and I said, well, in fact, Anna, the drag is even much more than you've calculated. So why not use this as a drag device and bag the ion thruster and just have it be a magnetic sail, and thus the magnetic sail. Now, the one thing about the magnetic sail, for it to perform well, you needed high-temperature superconducting wire that could do about the same kind of current densities that we could get with existing low-temperature superconducting wire. And in 1988, that seemed like that was going to happen soon because the field was moving fast. But since then, the progress in that field has been relatively modest. So the mag sail, while it has a number of important applications, and most particularly for decelerating an interstellar spacecraft, okay, because once it's going at very high speed, you could generate drag against the interstellar medium and slow down, and this would be a much more realistic way of stopping than trying to shoot at a light sail 4 light years away and reflect back at the other sail and do that. Okay, so there it was, pretty good. But then in 2004, Jan Hunen, a Finnish engineer or scientist, I don't know him, but he came up with this idea of an electric sail, which was you have a bunch of wires or a screen, and you charge them up positive, and here comes the solar wind, and it would be repelled by the positive charge and produce drag, which it could be used to maneuver in a number of ways. And I was actually one of the reviewers at the Journal of Propulsion when that paper came in. And I liked it, although I had a number of questions, in particular the questions of, well, wouldn't the electrons all just come to the positive wires and neutralize them? And how do you deal with that? But he had a lot of math in there about getting rid of the electrons with electron guns, and the fact that most of the electrons would actually miss the wires, because even though they'd be attracted to the wire, they'd have hyperbolic velocity with respect to it, and they'd keep going, and so on. So I recommended it for publication, and it was, and then it went out to the community, and people at NASA, at Marshall, have looked at it, and it looks like it could work, and I understand that they're actually planning a possible test flight of it. So that's very exciting. But the one thing about the electric sail is, once again, it's just a drag device. And so it has limited application. And then there's some other things here that I won't talk that much about. But I looked at the electric sail, and I started thinking, how could we fix this? And so I came up with an idea, which at one point I called an enhanced electric sail, but now I call it a dipole drag. It's a much cooler name. And here's how it basically works. It is an enhanced electric sail, but you have two grids, one positive, one negative. Okay? Now, here you come. This could operate within a magnetosphere, within interplanetary space, within interstellar space. So long as there's a plasma wind relative to the spacecraft, it comes in. These two screens are each charged. Outside of the screens, there is no field, because the electric fields of each of the parallel screens neutralize each other. Okay? But between the screens, there's a strong electric field going from the positive to a negative. Now, a proton approaches this, not knowing there's anything there because there's no field outside of it, and goes through the screen. All of a sudden, it's in a powerful electric field, shooting it towards the negative screen. Almost all of them miss the screen because it's, chicken wire, it's diffuse, and boom, shoot out the back. The electrons, on the other hand, are reflected, so they actually exert a drag, a counter thrust. Okay? And in principle, there should be a way to get some power out of that, but I don't address that. But anyway, it takes power to do this. You are accelerating protons with an electric field, but you are creating thrust without propellant. And the electrons go this way, the protons go that way. The electrons go much faster, but the protons are far more massive. The protons are 1,800 times as massive. The electrons are going 40 times as fast, so you actually have a net thrust. The electrons only neutralize 2% of the proton thrust. Okay? So there you have it. Now, if you did want to use a drag device, reverse the charges, in which case the protons will be reflected, the electrons will be accelerated. So you can either speed up or slow down. If you turn it at an angle, you can generate thrust obliquely to the direction of motion. So you can generate lift, that is to say, a force perpendicular to the wind. So you can generate force with the wind, against the wind, perpendicular to the wind, in fact, in any direction whatsoever. Now, let's skip all this. All right, so there's three regimes in which this could be used. Geocentric or planetary space around a planet where the plasma is the densest. Interplanetary space, where it's less dense. And finally, interstellar space, where it is less dense of all, but where, in principle, you're moving much faster, and that helps. Now, here is the dipole drive operating in Earth orbit. Now, in low Earth orbit, you have the upper ionosphere, and it is, pretty dense material as space plasmas go. And you can generate a significant amount of thrust. And this is for a 500-watt system. These are millinewtons. So if you want to know how many millinewtons per kilowatt, just double this number. So you've got 100 millinewtons per kilowatt at 400 kilometers if you use 1 volt. Now, if you go to 4 volts, okay, the size of the screen goes down. Okay, that is, the area of the screen is inversely proportional to the voltage for constant power. The thrust for constant power goes down with the square root of the voltage. Okay, so the radius is going down with the square root of the voltage, and the power is going down as the square root of the voltage. Now, if you go to a higher altitude, the ionosphere thins out, things get worse, you need a bigger screen. And you'll notice that at 700 kilometers, I don't even look at these very low voltages because the screens would be enormous. But okay, at 64 volts, the screen is, okay, in this case, 300 meter radius, and it's still 14 millinewtons per kilowatt. So that is an order of magnitude more than what is claimed to have been achieved with the EM drive, but it's all within existing known physics. Now, if you keep going up, it gets worse, both because the plasma is thinning out and also because if you're in a circular orbit, you're going slower. Okay, so if you want to, so if you're just maneuvering between 400 and 700, or trying to deorbit a satellite from 400 to 0, this works fine. Okay, but what if you want to escape? You don't just keep thrusting, you only thrust at near perigee. And you do a bunch of perigee thrust arcs, so the bottom of the orbit stays close to the Earth, and the top goes looping out, and you're not thrusting then. And then eventually you will escape the magnetosphere, and then you'll have available to you the solar wind. And the solar wind is much thinner than this, but it's much higher velocity. And the dynamic force of the wind goes as velocity squared. And so while on net the dynamic force of the solar wind is less than in LEO, it's only less by about 1 order of magnitude. Okay. I will comment that this can be used in Earth orbit. It can be used in Venus or Mars or Jupiter orbit. There are ionospheres there, which are much denser than interplanetary plasma. So even though you're going at slow velocities relative to solar wind is 500 or 600 kilometers a second. Earth orbit is 8 kilometers a second. Mars orbit is 4 kilometers a second. Jupiter is above 20. So this is a good system for maneuvering around in planetary orbits of Earth and other planets of interest. Now, what about sailing interplanetary? Well, in this case, you actually, how do I do this? This one. Oh, this is it. Okay. So here I'm showing using this as a sail. And here's an interesting thing. The protons, so we're now reflecting protons, and you'll notice they reflect with the angle of incidence equals the angle of reflection. Okay? So unlike a mag sail or a pure electric sail, this can create thrust that is perpendicular to the solar wind, and therefore it can accelerate you to expand your orbit around the sun or decelerate you to orbit in from the outer solar system back in towards the sun or anything of the kind. You could tilt it, you could change the inclination of the orbit, you could do all these things. So you can thrust with the solar wind, against the solar wind, you can do all this kind of thing. Now, as I said, the solar wind it's like 5 particles per cubic centimeter instead of 1 million, so that's a factor of 200,000, but the solar wind is going 80 times as fast as Earth orbital velocity, and you square that, that's 6,000, and so it's, and then whatever it was, 200,000 divided by 6,000 is like 30, and you take the square root of 30 is 6, so that changes the radius of the sail from 50 or 100 meters to things that are like half a kilometer kind of sails. It's still a doable thing. We're not talking about sails the size of Jupiter or Saturn. We're talking about sails that are half a kilometer to a kilometer in size, being able to do this. All right. And this just gives you a sense. Now, as you go into the thinner mediums, you want to bring the voltage up, because the thinner you are, you have to keep the area of the sail down, and for constant power, the sail is inversely proportional to the voltage. But once again, here in this example of a 1 kilowatt sail, we're looking at, 2 kilovolts. You're looking at something with a diameter of about 1 kilometer, and it has in this particular example, it has a thrust to power of about 3 millinewtons per kilowatt. So that's a bit less than we could get in Earth orbit, but it's still quite tangible. Now, what about interstellar drive? Interstellar, the plasma thins out even more, from 5 or 6 atoms per cc to 1 atom per cc. But the characteristic velocities you're doing are much faster. And and by the way, unlike the mag sail or the electric sail, this thing can go faster than the solar wind. Its maximum velocity is not limited by the velocity of the solar wind. You can sail crosswind, and you can accelerate as much as you want. Okay, whereas the pure drag device can not go faster than the wind itself. Now it turns out, okay, there's a parameter that I call kinetic voltage. And what the kinetic voltage is, it's just a proton which is going at a certain velocity. What is the voltage to stop it? Or put another way, if it was accelerated through that voltage, what would its velocity be? Okay, and so this is the wind velocity, say, here at 1,000 meters a second, the kinetic voltage is 5,000 volts. At 2,000, it's 20,000 volts. So the kinetic voltage goes as the square of the velocity. Now, what should be the voltage of a sail for maximum optimum design? It depends whether you're accelerating or decelerating. If you're accelerating, we look at this chart here, and where's this thing? Okay, there it is. It's hard to see. Anyway, this is the power per unit thrust. It goes up with voltage. This is the area per unit thrust. It goes down with voltage. Now you see it, and there's a parameter I call zeta, which is the ratio of the engine voltage to the kinetic voltage that you're dealing with. At a kinetic voltage of 1, well, if the kinetic voltage is less than 1, the area is gigantic. If you increase the kinetic voltage to 3, the area drops down to a much more manageable level. And you can see, if you keep increasing it, it keeps going down, but the lion's share of the gain of area reduction has been achieved. The voltage, as the voltage is increased, the thrust per unit area, or rather the power per unit thrust, which is bad, goes up. You want this to be low. You want both of these to be low. But you can see it's not that much worse at 3 than it is at a half. So I say, roughly speaking, and depending upon how much power systems weigh and how much the screen weighs, you probably want a zeta of 3 for acceleration. Now for deceleration, where what's happening is the plasma is hitting the screens, okay, and you hit it with a voltage, what happens is once you get to zeta greater than 1, you don't get any further thrust by increasing the voltage because you're just reflecting the plasma that's hitting it. Okay? In other words, the bullet's hitting the wall and it's bouncing off, and it bounces off with the speed that it hit the wall, and it doesn't matter how hard the wall is. If the wall is hard enough to reflect the bullet, then you get twice its momentum, and making it twice that voltage doesn't add anything to your thrust. Okay? And also, though, in terms of power per unit thrust, that's the blue line. It goes here, and then as soon as zeta hits 1, bang, we get reflected protons, and that cuts the power per thrust in half, but then after that it goes up again. So for deceleration, the optimum zeta is 1. Okay? Because you want the voltage of the engine to be equal to the kinetic voltage, or maybe 1 times 1 for safety. And then here is using this thing for missions. So how fast are you going? For how long do you do it? In this case, we're looking at acceleration. So the kinetic, the zeta is 3. The voltage of the machine equals 3 times the kinetic voltage. So for instance, at 500 kilometers a second, the kinetic voltage is 1.3 kilovolts. So we have 3.9 in the machine. And in 6 years, it would make it to 300 AU. Now this, okay, an assumption here, a jazzy assumption. I'm assuming the spacecraft has a mass per power ratio of 1 kilogram per kilowatt. That's dicey. I have attacked Franklin Chang's Diaz for making such an assumption in his Mars missions design, because it's ridiculous to talk about near-term power systems that have that. But if you increase that, the time goes as the square root of the mass to power ratio. So if we went to 50 kilograms per kilowatt for the spacecraft, including the engine, which is a doable thing, then the time would go up by a factor of 7. So instead of 6 years to reach 300 AUs, it would take 40 years, which is attractive. Okay? And so that's a doable thing. Now, if we start to get to true interstellar velocities, what happens is we have to go to higher and higher voltages. The screen size actually goes down, but the thrust to power goes down, and the performance decreases. So you start getting longer and longer times, even assuming a very aggressive 1 kilogram per kilowatt mass to power ratio. To try to get to 1% the speed of light here, it would take 200 years, and 2% the speed of light, 800 years. So this does look good for getting to the 550 AU mission. It's not so hot. Unless we can have much lighter power sources like beaming power to it, that could change this. Oh, gee, I'm out of time. So anyway, here it is, and I'll just go back to a simple slide so that anyone who missed it can see the basic idea of how this works and understand that this does obey the laws of physics. Thank you.